my pleasure, Dave. My pleasure still. Hey, all right. For the lunch talk today, we have David Banks from Statistics here at Duke. David has worked on a remarkable range of things, everything from baboons for grooming each other to the spread of mysterious, as to be unnamed, addictive substances through the Appalachians, to problems that have to do with agent-based models. And has been a friend of DNAC for ages. And so given that we just finished Sienna, I know this was a modeling feature, I thought it'd be nice to end up sort of our modeling thing, thinking of what's sort of the cutting edge of where new modeling directions are moving and have moved for a while. And so we're going to talk about agent-based models. So Dave,
thank you, Jim. Good afternoon, everybody. I'm going to say a few words to frame things because I have repurposed an older talk, but really the things that matter most to you all, I want to make sure that those are obvious. One is, if you are trying to build a model for social network relations, you can try and build it from using gender and age and all the usual types of features that people capture, but that really is not going to do a good job of getting the full complexity of human interactions. We interact for a whole lot of reasons. Some of it's random, but some of it is based on real data, but it's just subtle. And so simple models, such as we have seen with ergoms and so forth, aren't going to do a good job. Agent-based models offer an opportunity to try and capture much more complex interactions, and that's good. And my other framing message is that statisticians are letting you down in a big way because we have not yet developed the theory that says how you assess goodness of fit in an agent-based model. We don't know how to make predictive inference from a goodness of fit model. We don't know how to fit parameters to an agent-based model. So those are all major research challenges that are only now beginning to get a little bit of attention, and they're sincerely hard. So first of all, agent-based models are ubiquitous. They arise in all sorts of situations, and they occur when one wants to define low-level rules for behavior and then look at emergent behavior that comes from the ensemble of all of the agents operating together. Examples of agent-based models include weather forecasting, in which case each agent is a cubic kilometer of atmosphere and it interacts with its neighbors to exchange pressure, temperature, and humidity according to laws of atmospheric physics, and then you put that together as an ensemble and you see a weather front moving across the United States. In auctions, the agents are bidders. These are little programs that respond to a keyword, and they have rules that say how much they're going to bid, and the interaction is very simple. They all bid, one of them wins, and that's the ad that gets shown by Yahoo or Google. Transims is a program for modeling automobile traffic in cities that was developed by Los Alamos. And the agents here are all drivers, and they interact with each other by spacing their cars in certain ways and adhering to the speed limits or not, or otherwise engaging in traffic. And finally, perhaps people don't appreciate this fully, but genetic algorithms represent another category of agent-based models. If you know what a genetic algorithm is, then it's probably pretty obvious how that works. And if you don't know what a genetic algorithm is, I only have 50 minutes, so I'm not going to talk about it now. Agent-based models began back in the 1940s with ideas by Stanislav Ulov and John von Neumann relating to cellular automata, which are objects that interact with each other according to a fixed set of rules, usually on some very rigid grid. And the example is J.H.W.H. Conway's Game of Life. J.H.W.H. Conway's Game of a Life is a set of rules that says you have a grid paper, and the grid fill can either be black or white, and if you have too few neighbors, you die out. If you have too many neighbors, you die out. So a black spot will turn white if it has too few neighbors or too many neighbors, but if it has an intermediate number of neighbors, then it will stay black. And if you're a white cell surrounded by other black cells, then you will turn black. And it turns out that this can lead to long-term stable behavior that some people find very interesting. The field morphed into interactive particle systems, and you had people like David Griffith and others who used ideas from statistical mechanics to describe how that works. So these particles all interact with each other. That's fine too. But now we're moving forward into more complicated application where you have when you're beginning to scale up to the level at which you can begin to talk about social network applications. And that's where we are now. And one of the things that is driving the universal use of agent-based models is that people find them easy to code up and easy to face validate. They're easy to code because you simply have to prescribe what the rules are for the interactions of the agents and perhaps the geography in which the agents interact. We'll talk about that more in a minute. And the face validity means that you look at the rule set for the agents and you think, is this good enough? Does this capture the complexity that I'm trying to model? And if it does, you have some confidence going forward. Contrast that with the old school approach in which you would write some ordinary differential equations down for how things would work, and you'd look at the equations and your ability to sort of face validate those equations. Are they really capturing what's going on? That's harder to understand. Agent-based models are computer intensive, so they didn't become widely used until the mid-1990s. A major impetus for them was Growing Artificial Societies by Epstein and Axtell. And they were able to show that simple rules for the interaction among agents could generate very complicated behaviors that mimicked those that we see in real-world human societies. And what they did was they imagined that you had this large, an infinite flat plane in which sugar grew at a fixed rate. And the agents would wander around the plane consuming the sugar. And when they had eaten all the sugar at a particular place, they would move to a new spot that had more sugar on it, and they would eat that sugar. And slowly the sugar would grow back, and they would wander around in this space. And it turns out that the very natural outcome of, if you run out of sugar, look to the place that has the most sugar nearby and go there. That rule led to circular migration patterns, which mimic the patterns that we see in hunter-gatherer societies, who will go from the banana tree over to the potato field, and they'll just walk around their territory in these patterns. They added rules to generate additional complexity. They added sex, and when there was sufficient sugar, the agents could reproduce, and that led to population pyramids, carrying capacity, tribal growth with co-movement of families, and all the sorts of demographic features that we see in human populations. Then they extended the rule set a bit more. They added spice. So there were two types of resources, sugar and spice, and places that had lots of sugar tended not to have much spice, and vice versa. And so they wound up with the barter economy evolving or emerging from simple rules that if you have a lot of sugar but no spice, and somebody else has a lot of spice but no sugar, then you trade. They added tags, which mimic the idea of cultural memes that are transmitted, and so they were able to have sort of religions sweeping through the sugar scape. And they also developed rules that led to combat, division of labor, disease transmission, and other sorts of features that really were quite remarkable. Here we see the hunter-gatherer patterns. They're moving around in circles, and the radius of the circle is dependent on how quickly the sugar regrows. Here is a graph that shows conflict on the sugar scape. The different colors correspond to different memes that these agents have. The agents interact, and by chance, it turns out that blue winds up to be the winning meme, and eventually it basically takes over the entire sugar scape. So, at a high level, ABMs typically entail many agents, often with differentiated roles, and thus different sorts of rule sets. They have rules, which may be complicated. Sometimes the rules are heuristic, and sometimes they have randomized rules. They learn and adapt. Agents learn about their environment, and they also learn about other agents. I'm going to go back and expand on all this in a minute. There's an interaction topology, and this defines which agents affect which other. And usually this is in the sugar scape, that's a propinquity, but in a social network, it could easily be that you have a friendship relation with somebody else, and so there's some flow of memes or whatever between you, even if you're on opposite sides of the country. And then finally, you have the non-agent environment, which in the sugarscape example was just the sugarscape, but it could be something else. Not all agent-based models have all of these features, but these are the common ingredients that you see. One example of a way in which agent-based models are used is to predict the time it takes to evacuate a building. So what a civil engineer might do is basically feed in the building diagram that defines the environment in which the agents interact. The agent-based model randomly distributes agents within that building, and then they have a fire alarm going off, and the agent follows a set of rules. And that set of rules might be go to the nearest exit and leave, or it might be go to the nearest exit. If that exit is blocked, go to the next nearest exit. If that's blocked, go to the next nearest exit and continue. You have more complicated rules that may say go and get your laptop, then leave the building. And you can have differentiated roles. You might have a fireman whose role is to say, don't go this way, go that way. And if you have a fireman role, then the other agents will presumably do what the fireman tells them. The rule sets can be randomized. When the fire alarm goes off, the agents toss a coin, and some of them go and get their laptops, and some of them go to the nearest exit. You can learn, because as you go to the nearest exit, you can see that it's blocked, so you've learned something about the environment, and that means you have to do something else. You can, the interaction topology, that has to do with things like how many people can go through the exit at one time. So you can't pass through somebody else on a stairwell. And so those are all things that people do, and the goal is to try and get a distribution of how long it takes people to evacuate from a building, and if the median evacuation time is less than 10 minutes, then the building is well designed and has a sufficient number of emergency exits, and otherwise the architect has to go back to the drawing board. An early example of agent-based models that I really enjoy is a model by Stanley Kaufman, in which he looked at interactions among a set of genes, or for our purposes, simply a network. And so you had a randomly connected network in which each node in the network would receive inputs from the other nodes and send outputs to other nodes. And so the inputs were either 0 or 1. He was imagining a gene that was turned on or off, and he wanted to develop Boolean rules that would describe how you would take the inputs you get and generate an output. So here we have a model here with 8 different nodes, and some nodes link to themselves, some nodes link to other nodes. You have lots of random connections there, and at each time step, each node is sending either a 0 or 1 according to the Boolean table over here. So this particular node, 7, receives 3 inputs, one of which is from itself, and if all the inputs are 0, it produces a 1. Then it transmits to the nodes to which it is connected. Different patterns of inputs lead to different patterns of output, and that Boolean truth table is randomly assigned to each of the nodes. So there's a certain number of Boolean tables out there. One of them is randomly picked for node 5, a different one is randomly picked for node 6, a different one is randomly picked for node 7, and you just want to study the mathematical properties of these randomly connected networks. It turns out that when you have networks like this, you develop stable behaviors. So you'll have a pattern of 0s and 1s being sent around, and that pattern will recur. And once you fall into that basin, then you have a unique cycle, and in the biological sense, if you happen to be in one particular cycle, then you may be generating muscle tissue. If you happen to have gotten a different cycle, fallen into a different basin, then you're developing neural tissue. And the question is how many different basins there are. Here is a simple attractor. I'll talk about Garden of Eden in a moment. Here, you might start over here. Each one of these little dots is a initialization of 0s and 1s. So you've got a long vector of 0s and 1s that say what each of the nodes has. If you start here, then you go to this node, you go to this node, you go to this node, and eventually you wind up in this attractor. So you're in the basin of this attractor if you're in any of those states. You get pulled into here, and you're stuck. You simply go around and around that circle, repeating the same patterns of 0s and 1s infinitely often. The Garden of Eden state refers to a state that you can a stable state that you can begin in, but which you cannot reach from any place else. So once you leave the Garden of Eden, it's all over. And the reason that's technically not a Garden of Eden is because this is not a stable state. If you start here, there's no chance of persisting here. You have to continue on all the way until you reach this attractor. Yes. One of the nice things about these attractors is it turns out that they're really quite robust. If you add a little bit of noise, so you have the stable cycle going around, but I just arbitrarily change one of the zeros to a 1. That throws you outside of the attractor, but you're usually still in the basin of the attractor. And so you might get sent off somewhere else, but you'll trickle back to that attractor again. You have to do a lot of random perturbation before you can get out of your current basin and jump to another basin. But biologically, this is not impossible, and it corresponds to the fact that if you look at muscle tissue, you'll sometimes find, a nerve cell sort of in there by accident. And so it is possible for odd types of tissue to occur by chance. Now, we're going to look at the number of attractors and the number of cell types. So, mathematically, this would be the number of attractors if you have this many genes, this many nodes. And for various species, you see the number of different types of tissues that they have lined up against the number of genes. And so what we're seeing is that those look rather similar. It does seem as though a randomly wired network of Boolean agents can produce about the same number of tissue types as we see in animal populations. We note that animals tend to have a little bit fewer numbers of tissue types than the randomly connected network would give. But I think this is not unreasonable because we have evolutionary pressures to have stable attractors. And so if we reduce the number of attractors, that increases the number of random perturbations it requires to get us out of one basin into another. So this is evocative. It's not a proof, but it shows how a biologist can think about agent-based models and develop interestingly useful heuristics to help think about his field. Obviously, the problem in all of this is going to be verification and validation. You'd like to have some way of deciding whether or not the model that you've created, your agent-based model, is sufficiently faithful to reality to actually provide useful insight and information. And you'd also like to verify that the code is correct. And both of these are problems. I'm not going to dwell on the verification problem because I think that's a little bit outside the ambit of our interest today. But the validation problem is certainly one that all scientists should be concerned about because we model things all the time, but we have to ask how good is our model. There's a hierarchy of validation strategies from physics-based modeling all the way to comparison to the real world. None of these are really fully satisfactory. And as I said, statisticians have fallen down. We have not invented a goodness of fit test that will really help solve this. But we're sort of working on it, and there's some ways forward that I'll talk about a little bit later. Physics-based modeling is when you think that you really know what's going on in the problem, and you are just modeling it from first principles of physics. And this is probably a good strategy when you're trying to look at planetary motion. We think that we know the laws of gravity, we feel confident in those. I have a batch of agents which would be planets or comets or things like that, and they would all interact with each other through their gravitational fields, and I'll predict where the agents are going to be at the next time click by simply applying the laws of physics and showing where those masses have to move. There are other places where you think you know what's going on. Agent-based models have been used to describe semiconductor manufacturing and flight simulators and stuff like that. And in those situations, that's probably pretty good. But when you begin to have randomness in the system, not so much. Intelligent design is what people, it's my name for it, obviously. But the idea is you think hard about the problem, you try and build on everything you know about what this system you're modeling is, and then you encode the rules for the agents to reflect that knowledge. And this is probably done in lots of situations where you don't have a whole lot riding on the output. For example, the case I gave of the civil engineer who's trying to predict how long it will take people to evacuate a building, well, they're not going to spend a lot of time trying to validate this model. They're not going to put people in the building and evacuate them 100 times and see how it works and sort of, mirror it against the real world. That's not practical. Instead, the civil engineer or the programmer who's working with him is going to look at the rule sets for the agents, looks at the geometry of the building, checks it out to see if anything weird is happening, like people passing through each other and so forth. And if none of that's going on, then they're going to clear it good enough and move on. And this is probably not bad. It's cost effective, and if you have relatively simple cases, that probably works pretty well. My guess is that this is the same type of thought process that goes on when writing computer code, and so the output that you get are going to be comparably buggy to what you have when you write code. And, often it's good enough. Face validity is sort of the first one with a sort of an explicit validation protocol. The designer tests the simulation by using selected inputs to explore the output behavior. And if you really want to get serious about this, you may use some statistical experimental design to decide which inputs you're going to test so that you fill out the space of all possible inputs. If you're trying to do the weather forecasting model, where your agents are cubic kilometers of atmosphere, you might try setting the system so you have hot air over here, cold air over there, and you watch the inputs propagate, and you watch the weather front propagate along. It becomes harder if you decide you're going to have hot air, cold air, hot air, cold air. That's not really physically reasonable. It's not the way weather typically works. So testing at those initial conditions, probably not a smart thing to do. But in Latin, a Latin hypercube might try and give you that as a prescribed input. So there's both art and science involved in doing this type of face validity check, but we have ideas about how to do this, and we can do good ones and bad ones. This type of stuff is used in episims and the battlefield. Episims is related to transims, the automobile traffic model. It was bootstrapped up to describe the spread of disease in a population. So they're using epidemiology to study how things spread. And basically, they took the old model they had for traffic, and they simply gave some of the people the disease, and every time they arrived at the same location, there was a certain chance of transmitting the disease, and they watched how it would spread through a city map. And the Defense Modeling and Simulation Organization is a branch of the DoD that does battlefield simulations to study things that generals care about. And both of these make extensive use of agent-based models, and they do have these sort of face-valid protocols in which they will have some general come in and they'll say, if we put the tanks over here and the flamethrowers over there and the civilian population here, what will happen? And the general will say, well, I think this is going to happen. And if the simulation reproduces that, then it's been validated to some degree. Comparison to, oh, yes, please.
Well, I used to work in that space, so I generally agree with you that they're over-dependent on subject matter experts. We do try to do like X-stone, rods, docking, paper kinds of strategies, and talk about sort of different forms of equivalence and things like that. And so, not to be overly defensive of the digital form, but in any event, so I mean, I think it's fair to sort of talk about docking strategies in general if you're talking about these kinds of agent-based models.
Thank you. You're right, and I am being a little glib about all of this. But it's a fundamental problem. They do have to rely upon experts. The experts are notoriously overconfident. Getting any sort of
Agreed.
yes. Okay. So often, well, no. Sometimes one can compare it to another model. And if you have an agent-based model and some other model, then you can see whether they agree or disagree. And if they disagree, you can try and figure out which one you think is doing the better job. In weather forecasting, we have an agent-based model, but we also have stochastic differential equations that describe how things are supposed to flow, because the atmosphere is basically like a liquid, and you want to see how things go there. So you would have alternative models that you could use and compare and see what makes sense. We'll talk a little bit about the Reed-Frost differential equations model for disease spread, where we have exactly that situation. And finally, there's a comparison to real-world results. And this is probably the best test you can do, but often we don't have enough real-world results to actually make that definitive. HAZUS is the flood damage model used by the United States government to set insurance rates all over the United States. And I contacted the office, it's the FEMA, who have this model, and I asked them, what can you tell me about the model? We can't tell you anything, sir. It's a proprietary model that was developed by a contractor. And I said, great. Can you tell me how many statisticians were involved in this? And the answer was none. And and having worked in the federal government, I can assure you that there's a wide range of capability among contractors, and it's not at all obvious to me that this HAZUS model, which plays such a critical role in determining how much people pay, has any real basis in reality. And in particular, it fell down very, very badly when Hurricane Katrina rolled through, and all the predictions from the HAZUS were wrong. And in fairness, when you have a situation in which the levees, overflow and stuff like that happens, things are going catastrophically wrong, and the model that somebody dreamed up in a contractor's office somewhere outside the Beltway is probably not going to be robust. But we have lots of floods. We can check to see how the HAZUS model works in many different locations, and it turns out that those 100-year floods that HAZUS talks about come along about every 20 to 30 years. So there's some miscalibration going on in there somewhere. Another difficulty with trying to use the real world is that you're often interested in extreme or rare events, and so you really don't have enough real-world experience about those to be able to have much confidence in the real world's ratification of the model. I said I was not going to talk about verification, and I won't, except to say that many agent-based models are large, complex things. The code is never going to be perfect, and that's going to be a problem for lots of people. There are strategies on how to improve that, but we're not there yet. So, I'd like to think some more about validation, and being a statistician, I think about it from a standpoint of parameterization. And all the simulations that one has, agent-based models or other types of simulations, rest upon parameters. And these are often chosen for ease of development and coding rather than for how well they correspond to reality. And in traditional mathematical models, like stochastic differential equations or so forth, these parameters are going to be coefficients and the seeds for the simulation. In agent-based models, they're going to be parameters for each agent, basically the rule sets for the agents. And then you have other situations where the parameters are slightly different. Often the behavior of interest can be globally high dimensional but locally low dimensional. So let me see what is a good way to explain that. Yes, suppose I have 100 coins, and one coin has probability 0 of coming up heads, one coin has probability 1 out of 100 of coming up heads, one has probability 2 out of 100 of coming up heads, and so forth. And I randomly draw a coin and start tossing it, and what I observe are the results of my tosses. If I try and describe the entire system, it's got 100 different parameters, one for each coin. But as the process continues, it turns out that locally, for a particular choice of a coin, it simply has one parameter, the probability of coming up heads. And so you can have global complexity, but local sparsity. And in general, if you don't have some sort of locally low-dimensional behavior, you're really not going to be able to understand the phenomenon that you're caring about. It's just going to be too complicated, and you should phone in sick that day. So, as an example of what's going on that illustrates some of the ideas we've touched upon, this is I said it's going to be Reed Frost, actually we're doing the Kermit-McKendrick model for disease spread. I of t is the number of people who are infected with the disease at time t. S of t is the number of people who are susceptible, who have not been infected but could be. And R of t is the number of people who have recovered after being infected. And a very simple set of differential equations describes how these numbers change. And it turns out that the rate of increase in the infection is proportional to the product of the number of people who are infected and the number of people who are susceptible. If half the people are infected and half the people are susceptible, then you're going to have the most rapid rate of change because there are a lot of people who can infect and a lot of people waiting to be infected. But as you get towards 0 or 1, everybody's infected or nobody's susceptible, then it slows down. And if you look at these equations, you see that there are really only two parameters going on there. The lambda, which governs the infectivity rate, and the gamma, which governs the recovery rate. And so really this system has just two parameters walking along that govern the entire behavior. However, many epidemiologists have developed agent-based models to describe the transmission of a disease. And that's not crazy, because agent-based models do allow the possibility of a more microscopic understanding of the actual way things happen. For example, if elementary schools are a nexus for disease transmission, you can build a model for a community in which there are families with children and they drop them off at the school. The kids, catch malaria, come back home, spread it to the family, and it goes from there. And you can build in other types of structures as well, so that people who work in the same office building are, more likely to infect each other. And that's actually useful knowledge because you can begin to understand when it makes sense to close an education system down until an epidemic is passed, as they did with the Spanish flu. It can make sense to figure out that, if you're sick with the norovirus, don't go to the hospital. That's a really bad idea. So you can figure out useful public health responses from the agent-based model that are not visible from the differential equation model that we have here. Nonetheless, qualitatively, the differential equation model tells us that what's really going on here is basically you've got two parameters, and there'll be some wiggles and bumps that reflect the effect of elementary schools and the effects of hospitals and so forth. But those wiggles and bumps are not going to dominate the qualitative progress of the disease. It's going to be driven by lambda and gamma. So that sort of illustrates the tension of the situation. You have the mathematical understanding from the equation model, and you can compare that to the agent-based model. And this is a bit of a digression, but I enjoy criticizing epidemiologists, so let me quickly say that the differential equations models have only worked once. In all the applications that people have applied to the real-world data, it has only worked once, and that was in 1911 when there was a measles epidemic in Iceland. And at that time, nobody in Iceland had ever had the measles, so they were all susceptible. Measles is highly contagious, and there was one road that connected the three cities in Iceland. And you just watched the disease march down that road. So, yes?
Your example sort of brings out, though, why you might want to use the agent-based model, right? Which is that you have all these conditionalities that are all operating. You're not completely clear yet how the conditionalities are actually conditioning, so you don't have a nice function about how that's going to operate. And you might be able to build intuitions and build that function by looking at the simulation and maybe doing multiple simulations of population, all this good stuff. But
that's exactly right. There's real value from the agent-based models because you can do what-if experiments and you can identify things that are, matter from a public health management standpoint. But you also gain a lot of insight from the mathematical equation models because in some sense that tells you what the dominant behavior is. It's like the skeleton that you then build other complexity upon. So that's a lovely example of the the interaction between agent-based models and theory-based models. So how do we understand what the intrinsic dimensionality of an agent-based model is? We have a whole batch of agents. We have rules that those models, that those agents follow. There's qualitative behavior that we're looking at to try and understand. What is the approximate dimensionality of that model? And one way to think about this is to imagine that we have a parameter space that is a convex subset of a Euclidean space, and for every point in that parameter space, we'll produce an output from an agent-based model, or perhaps the expected value of an agent-based model if we do this with randomness. So each point in the convex set corresponds to an output in the agent-based model world. And we'd like to figure out what is the dimensionality of that convex space. And so one strategy for doing this is to run the agent-based model, ABM, many times, and we're going to let y sub I be the output of interest, how long it takes to evacuate the building, how long it is before the disease goes away, stuff like that. And so we'll start the agent-based models many different times. We'll run it forward. We'll have the initial conditions for the agent-based model. And what we're going to do is basically do a principal components regression on the k points. Yes, okay. We have a random set of inputs, the x's. We'll throw a ball down around that. We'll look at the output space. We'll do principal components regression from the inputs to the outputs. And we'll figure out how many principal components we need to explain about, say, 80% of the variation in the output space. So in this region of the space, it may be that there's only 3 principal components that are needed to explain 80% of the variation in the output space. In another region of the convex set, it may be that there are only 2 principal components that are needed to explain the variation in the output space. And I could average over all of those balls, and I might get 2.5. And then I would say that the average intrinsic dimensionality of my agent-based model is 2.5. And I can elaborate on this a little bit. I won't go into too much detail, but I'm going to introduce a Q cube in RP, a 1 cube in R2, so R2 is the plane, a 1 cube in R2 is the perimeter of the square. A 2 cube in R3 is going to be the faces of a regular cube. A 3 cube in R3 is the entire cube, the interior and the faces and the edges. And so here is a 1 cube in R3, just the edges, and I've randomly sampled from that from its boundary. This is a 1 cube in R10, also tilted 10 degrees out of alignment. And when you look at this, you can no longer see the really interesting low-dimensional structure that we know is there. So here, the low-dimensional structure is obvious. The same structure exists here, but we're not going to see that by inspection. We're going to have to use something like this principal components regression trick that I described earlier. And if you'll allow me to use a prop.
David, while you're putting your prop together, I have to ask you, something with some coloring there. I mean, isn't on some level the 3D one easy to see because there are only 12 line segments, and so like we can pick that up. But I mean, now I forget my basic geometry. You're gonna have to tell me how many line segments there are in a 10-dimensional hypercube.
Well, certainly there are more of them, but also we aren't set up to perceive that. And there's a theorem that says actually any structure in a high-dimensional space will almost always give you a projection to a low-dimensional space that looks normal. Okay. And that goes back to Diaconus and Friedman. Okay. And so, so that's fundamental. Okay. I've made little blue dots here, and here it's clear that it's a low-dimensional structure. It's a 2-dimensional surface, so all of my dots exist in the 2-dimensional space. If I crumple this up loosely, make the napkin transparent, and all that you can see are the blue dots, it will look like the blue dots are up there. But if you look very closely, you'll see that a lot of blue dots fall on this little surface. Then you turn a corner, and you have maybe 3 dimensions instead of 2. Then you have another 2-dimensional sheet, and So except when you go around one of the loose crumples, you have two-dimensional structure. So that's an example of a situation in which you have intrinsically about two-dimensional structure hidden in a three-dimensional space, and with agent-based models, the problems get worse. This is getting too tedious, but if you have Q cubes in P space, and you want to recover them, the principal components regression method that I talked about does a pretty good job. If you have one-dimensional structure in 1, 2, 3, 4, 5, 6, 7-dimensional space, you'll see that your estimate of the intrinsic dimensionality is pretty stable and pretty close to 1. For if you have two-dimensional structure, the surfaces of the cube in 2, 3, 4 space, you're getting numbers that are, again, pretty consistently. They're always an underestimate because we're explaining only 80% of the variation, so we know we're biased down. But nonetheless, we could unbias that pretty well, and I argue that this shows that one, in principle, can find the intrinsic dimensionality even from a very complicated agent-based model. So we can build an agent-based model that describes disease transmission, and I bet that if we took the outputs from that model, ran it through something like this, we'd find that there's basically two dimensions, the lambda and the gamma, that are driving the broad brush behavior of the system. One thing that is counterintuitive, and I won't dwell on this, is the seed that generates the simulation. In order to have random numbers, you want to have sensitive dependence to the initial conditions. And so if you change your seed just a little bit, you want to get some wildly different string of random numbers that you generate. However, that makes it very hard to do the validation that we care about, because a whole lot of apparent noise is being introduced by changes in the seed. So my recommendation, if you are validating an agent-based model, is to test it, validate it, using something that doesn't have sensitive dependence to the seed, so that the seed changes very smoothly, and then when you want to do it for real, then you take out that random number generator and plug in a real random number generator, and then you will be able to get a better sense of how the ABM will behave. So validation is easiest when the parameter set for the simulation is a convex subset of the Euclidean space, where it's smoothly related to the outputs and where it's low dimensional. Smoothly related to the outputs is not something we have talked about yet, but if you imagine you have got a agent-based model for evacuating a building, you can imagine that the agent comes to a corridor, tosses a coin, and can turn left or turn right. That's not smooth, and it leads to qualitatively very different outcomes. However, if we're talking about the weather forecasting model, there you are smoothly dependent upon the parameters, because the temperature change is smooth. The temperature changes smoothly, pressure changes smoothly, moisture changes smoothly. So if it's smoothly related, if the parameters are smoothly related to the outputs, then you're in a much better position. We talked about low dimensionality. In statistics, there's something called the Curse of Dimensionality, which says that your predictive accuracy becomes super exponentially worse as the number of parameters increases. And that's why I still feel that you should always hope that you have locally low dimensional behavior, because if you don't, you're really not going to be able to make any headway with the problem. And in the context of social network modeling, that's not crazy, because if whether or not somebody becomes friends depends upon 200 things, you'll never be able to understand what's going on in that social system. It's just too complicated. You hope that for the system you're studying, there are a few major dominant factors, and you can pick those out. Yes, often people will write separate models. You'll have even two different agent-based models written by two different people. And then the question is one model a proper subset of the other model? Does one model reproduce the other model? What are the relationships between them, and how can you tell? And there is a certain amount of topological theory that basically says if every open set in one model input space maps to an open set in the other model space, and they all contain each other in the right way, then the two have to be equivalent, which got my graduate student his PhD, but did not advance the field in any meaningful way.
Except for the great work he's done since.
Well, yes. But that's really a hard problem, and it's really an open question. Trying to figure out when two models are equivalent and when they are not, in general, is really, really hard to do in the agent-based model world. If it's the equation-based model world, then it's much easier. I don't think I have anything important to say here. Model calibration. I mentioned at the beginning that one of the really hard problems with all of this is to try and tune your model. You've got an agent-based model, it's face valid, but you have these little tricky parameters, like how quickly does somebody run down a stair when there's a fire going on? How do you fit that based on some sort of empirical data or prior knowledge? And the good news is we now have a theory for how to do this. It is developed by Tony O'Hagan, and you have real world is what you observe. This is the real world model that generates it, and then you add noise to account for all the stuff that goes wrong in the real world. And Tony O'Hagan's model basically says what you observe is an emulator plus a discrepancy function plus the noise. And it uses Bayesian tools to try and estimate both the eta and the delta, and also to find the theta that is the tuning parameter that matches best with what's going on to the real world, how quickly people run downstairs. I won't get into all of this stuff. The remarkable thing is you can get a posterior distribution over the discrepancy function delta. And that tells you where your agent-based model is doing well and where your agent-based model is doing poorly. And it's pretty remarkable that you can do that. You need to have a little bit of real-world data to get there, but not a whole lot. You often need to have a lot of simulation runs from the AVMs. Those are generally cheaper, although some are really take a long time to run. But in principle, that looks like sort of the best way forward in trying to develop some statistical theory that will address agent-based models. And I am nearly out of time, so let me just jump to the conclusions. Agent-based models are an important new tool in simulation. They've become standard in many different fields, and we don't understand anything about how to use them in any formal way. A key step for ABM theory is better understanding of the parameterization, and ideally you're going to find a map from some convex Euclidean subspace to the output space. We have new ideas for how to calibrate agent-based models, and that, I think, is very exciting. We are learning how to express uncertainty better, but it's still not a solved problem, and it's a work in progress. Thank you all very much. We have time for some questions, I think.
Absolutely, yes. Questions for David? I have one quick thing. So I've written more than my fair share of completely ad hoc AVMs.
Yes.
And so I've struggled, with how much detail I add to those. Could I use this principal component analysis to essentially decide if I don't need the market tightening parameter or don't need this other parameter?
Yes, I believe you could. I've worked with scientists at RTI who've been developing agent-based models, and they just over-elaborate things ridiculously.
Yeah.
And so I really think that good judgment is the first starting point, because you don't need to model everything. But then you could use the principal components regression approach to decide if you were getting the ballpark of being sparse.
Because I think that's one of the critiques that, the first thing a reviewer says is, well, what about their favorite X? And it'd be nice to be able to say, well, if I do the parameter space, I can capture 85% of the variables with this set. I really don't need anything else or something.
Right. Another way of saying what you're saying, I think, is if your average intrinsic dimensionality is bigger than about 7, I don't know that you're going to find anything interpret this. Final question for them?
Stepping back question.
Yes.
So when we're interested in looking at and understanding complex phenomena, agent-based models, system dynamics models, and network analysis are kind of that trifecta of
personalities for bringing in feedback loops into the theory of social networks, because they weren't there until they thought of it, and clearly they're necessary. They play complementary roles, and I think it depends a little bit on what your objective is. Broad-based social theory, homophily and fundamental principles like that, I think are well understood from sort of the traditional equation modeling, and that's very helpful. The system dynamics models are good if you are trying perhaps to understand some particular behavior, like, for example, how people are going to vote in the upcoming election. There's clearly a social network happening in which people shift their interests and allegiances among the candidates, and perhaps system dynamics is sort of the way to capture that. But it's not going to capture it well at the individual level. And the agent-based model allows you to sort of drill down to an individual. If you're an unemployed white guy without an education, well, your social network may be inclining you to vote for Donald Trump, and the force with which it does so depends upon how many people around you are pushing, and your own temperament. Some people are just iconoclasts, and if my wife discovers that everybody agrees with her, she changes her mind. And there are people like that, and you can build that in. Now, you probably don't care about it at that level, but for certain social processes you do. Because, as we said earlier with the feedback loops, we don't wind up in a situation in which everybody in the community winds up believing the same thing eventually. If you start getting too close to people in your ideas, there's a tendency to step back. And that is something that I think can be handled at the individual level better with an agent-based model. Thank you. Well, I'm going to have to run. I've got a 1:30 appointment.
All right, thank you so much.